You might know that when an object rotating at a constant velocity, the centripetal acceleration of the object is given by v squared over r. But have you ever thought about how do we derive this equation? There are actually dozens of methods to derive this equation, but I'd like to discuss two of them in this video. One is a geometry approach, and the other one is a calculus-based approach. Let's first concentrate on the geometry approach to get a general idea of this equation. To start with, consider about the rotating object we saw at the start of the video, where O is the center of the orbital, P1 is the orbiting object, R1 is the position vector of P1, and our object has a velocity v1. After the object moves with velocity v1 for a short time delta t, the object has moved to the point P2 with the position vector r2. Since in a uniform circular motion, the speed of the object is constant, the magnitude of the velocity v2 remain unchanged, but the direction stays tangential to the orbital. Let's call the displacement delta r. We may also represent delta r as the product of v1 and delta t. In this case, let's only consider about the magnitude of the vectors. If we move v1 to make it becoming tail-to-tail with v2, we can actually create two right triangles, and r2 is also perpendicular to v2. From this, we can conclude that these two angles are equal, which is to say these two triangles are similar. So the change in velocity, delta v over delta r, is equal to v1 over r1. Then substitute v1 delta t for delta r and rearrange the equation. As delta t approaching 0, delta v over delta t becomes the acceleration of the object at p1. And here is the result we are looking for. After looking at the geometry approach, I believe that we've had an idea of this equation. However, the geometry approach somehow has some disadvantages, like it does not tell us what is the direction of the acceleration. So let's now focus on the calculus approach, which will be more precise and able to solve the problem left by the geometry approach. First of all, let's bring back the graph that we've seen in the geometry approach, but this time, I would like to use polar coordinates to help simplify the problem. So let's make angle theta the angle between the position vector of P1 and the horizontal. The radial unit vector r hat has the same direction with the position vector r, and the tangential unit vector theta hat is perpendicular to r hat, having the same direction with the velocity vector v. In this case, these two angles are also equal to angle theta. We can calculate the I hat component and j hat component of each of the unit vectors in the Cartesian coordinate. R hat equals to cosine theta I hat plus sine theta j hat, and the theta hat equals to negative sine theta I hat plus cosine theta j hat. What we now like to do is to take the time derivative of R hat. By the product rule, we get the time derivative of angle theta times the derivative of r hat with respect to angle theta, which we can calculate it and get negative sine theta I hat plus cosine theta j hat. Notice that the time derivative of angle theta is indeed the angular velocity and will represent it with omega. If we take a look at the latter part of the equation, we'll find out that this is just the unit vector theta hat. Similarly, if we take the time derivative of theta hat, the latter part will be negative r hat. Now, we would like to use the letter r to represent the magnitude of position vector r, which will just be the radius of the orbital. Then, we'll calculate the velocity by taking the time derivative of vector r. Substitute vector r. We can move out r since the radius is constant, and the derivative of r hat is omega theta hat. We'll use letter v to represent the magnitude of the velocity. By rearranging the equation, we get that omega equals to v over r. Lastly, let's calculate the acceleration by taking the time derivative of the velocity. We can substitute the velocity, move out r and omega since they are constant, substitute the derivative of theta hat, rearrange the equation, substitute omega, and eventually we'll get vector A equals negative v squared over r times r hat. The magnitude of the acceleration, A, will just be v squared over r, which matches the result we gained in the geometry approach. But this time we also get that the direction is negative r hat, which is said to be pointing radially inward to the center. And that is the reason why we call it the centripetal acceleration. That's all the content for this video. Thank you for watching it. If you like my videos, please subscribe to my channel. This is the first time I try to make animations, so if you have any advice, please leave a comment under the comment section, and see you in the next video.